We are now ready to discuss the relationship between probability and statistical inference. Recall that for purposes of this course, we define statistical inference as the process of making inferences on population parameters using sample statistics. We have two facts that are key to statistical inference. These are: population parameters are fixed numbers whose values are usually known, usually unknown, and secondly, sample statistics are known values for any given sample, but vary from sample to sample taken from the same population. In fact, it is nearly impossible for any two independently drawn samples to produce identical values of a sample statistic. This variability of sample statistics is always present and must be accounted for in any inferential procedure. Fortunately, this variability, which is called sampling variation, is readily recognized and is accounted for by identifying probability distributions that describe the variability of sample statistics. In fact, a sample statistic is a random variable, as defined earlier, and like any other random variable, a sample statistic has a probability distribution. This sampling distribution has characteristics that can be related to those of the population from which the sample is drawn. This relationship is usually provided by the parameters of the probability distribution describing the population. What follows in this lecture is to introduce the sampling distribution of the mean, also referred to as the distribution of the sample mean, and the sampling distributions of other statistics. Sampling distribution is the most fundamental concept of inductive statistics. Let us suppose that if we actually made an exhaustive survey, that is, if we actually measured the height of each adult male resident of the community, we would obtain the following distribution, whose mean is 68 and whose standard deviation is 3.44. What we have done here is referred to in statistics as exhaustive sampling. We actually obtained the entire population, 9,998 units have been measured in this exhaustive survey. We actually obtained the entire population, the height of all adult male residents of the given community. And we then found its mean without having to make any generalizations. In actual practice, statisticians seldom resort to exhaustive sampling, which covers the entire population. It is impossible for infinite populations and unfeasible if the sampling is destructive. We had discussed this earlier. Also, it is usually impractical and unnecessary since sufficiently accurate information can be obtained on the basis of relatively small random samples. For instance, if we had taken a random sample of size 5 and used its mean to estimate the population mean, we would make the generalization that the average height of all adult male residents of a given community is, say, 66.2 inches. We selected randomly 5 units out of a population, out of this exhaustive sampling, and found the sample mean as 66.2 inches. Having made a statement about the average height of several thousand persons, after having measured as few as 5 of them, we might well be asked any one or all of the following questions. Can we really expect a sample mean to be reasonably close to the mean of the population from which the sample was obtained? How sure are we that our sample mean will not differ from mu by more than 1 inch, 2 inches, or say 3.1 inches? And thirdly, anyone can ask, if we were to repeat this experiment and take several random samples of 5 measurements each, how closely could we expect their means to be clustered around mu? These questions are very important and they should be answered. But before we can do so, we must conduct a further experiment, specifically the experiment which was suggested in question 3. It is clear that we cannot reasonably expect every sample mean to coincide with the mean of the population. As a matter of fact, if we pick the distribution given on the previous page, we find that mu is 68 and that our estimate of 66.2 is thus off by 1.8 inches. If the sample mean had been 67.4, our estimate of mu would have been worse. In order to see how sample means fluctuate from sample to sample, let us take 50 separate random samples of 5 measurements, each from the given population, which, as you will recall, consists of the heights of the adult male residents of a certain community. The following are 50 such random samples, and the means of each sample. On the first column of first and seven columns of the table, the observation number, the identity numbers. Next 5 columns consist of the units of the random sample. Let's get the first sample consists of the units 70, 72, 64, 62, and 70, and on the 7th column the sample means 69.8, etc. The mean of these 50 samples is found as 68.032, and standard deviation of these 50 sample means is 1.66. Symbolically, we shall write x bar of x bars 68.032 and as subscript x bar equal to 1.66 using the subscript x bar to indicate that we are referring to the mean of and standard deviation of the 50 sample means x bars. In order to get an overall picture of the 50 means, let us group them into the following distribution. The following distribution is called an experimental sampling distribution. It consists of the means obtained in an experiment in which we took repeated samples from the sample population. Here we see the experimental distribution. The mean of these 50 samples is 68.032 and their standard deviation is 1.66. Okay. Corresponding to the experimental sampling distribution of the 50 means shown above, we might now ask, what is the probability of obtaining a mean which lies between, say, 67.5 and 68.4? What is the probability of obtaining a mean which lies between 68.5 and 69.4? What is the probability of obtaining a mean between 66.5 and 67.4, and so forth? A distribution which shows the probabilities of obtaining different values of x bars sample means is called the theoretical sampling distribution of sample means. If we could enumerate all possible samples of size 5, calculating their means, and constructing the theoretical sampling distribution of sample means by assigning each possible sample an equal chance of being selected, it would give us the probabilities of getting various values of sample means in a random sample of size 5. This would be an enormous task. Fortunately, it will not be necessary to perform the steps required to construct such a theoretical sampling distribution. Instead, we shall refer to two very important theorems about the theoretical sampling distributions of sample means. The first of these theorems gives us general formulas for the mean and standard deviation of a theoretical sampling distribution of sample means. Having a knowledge of the mean and standard deviation of the sampling distribution, the second theorem will enable us to calculate the probabilities of obtaining various values of sample means. The basis of these theorems is the law of large numbers. So, it's timely, before stating these two theorems, let us first state this law. The Italian mathematician Cardano Gerolamo lived between 1501 and 1576, stated without proof that the accuracies of empirical statistics tend to improve with the number of trials. This was then formalized as a law of large numbers. A special form of the law of large numbers for a binary random variable was first proved by Jacob Bernoulli, lived between 1665 and 1705, and his work, immortal work, has the title of Ars Conjectandi, meaning the art of conjecturing in English. He named this his Golden Theorem, but it became generally known as Bernoulli's Theorem. Further described it under the name what showed Bernoulli was, by taking the number of trials large enough, the probability that the result will lie between certain limits will be as great as we wish. He proved this statement. This theorem became generally known as Bernoulli's Theorem. Much later, 18 years later, Poisson, Simon, Dennis. Further described this law under the name La Loi des Grands Nombres in French, meaning in English the law of large numbers. Thereafter it was known under both names, but the law of large numbers is most frequently used. Recall that we have stated earlier, Bernoulli proved this limit theorem. This is the restatement of the what Jacob Bernoulli proved in mathematical notation. It says simply the difference between the parameter of a variable x and the sample statistics related to this parameter, the difference in absolute value, the probability of the error of estimate. We use sample statistic Sx for the estimation of parameter x. So this deviation from the actual value of parameter, this sample statistics, is called the estimation error. The probability of estimation error is less than a positive number, a small, very small indeed, a number, symbolically epsilon. The probability of estimation error or sampling error is less than epsilon approaches to 1 as the number of trials approaches to infinity. To state the law of large number in a modern fashion, let X stands for a measurable attribute of individuals in a finite or hypothetical population, and let P subscript X stand for the true value of a parameter supposedly calculatable by enumerating a population of X, as subscript X stands for the corresponding sample statistic obtained from random sample of size n. Then we can write for any positive number A this limit. This version of law of large number is referred to as weak law of large numbers. Interpreting this result, the weak law states that for any non-zero margin specified no matter how small, with a sufficiently large sample, there will be a very high probability that the average of the observations will be close to the expected value that is within the margin. It can also be written as indicated in the formula 72.1.1, which states that the sample statistic converges in probability towards its expected value, that is the parameter Px. On the other hand, the strong version of law of large numbers states that the sample average converges almost surely to the expected value. That is, now the probability of the limit is equal to 1. The probability of the stated limit equal to 1. What this means is that the probability that as the number of trials n goes to infinity, the average of the observations converges to the expected value is equal to 1. Here, we shall not dwell into the proofs of law of large numbers, which requires the use of calculus. They can be found in any textbook of mathematical statistics. Now, we can return to the theorems about the theoretical sampling distributions of sample means. The following theorem enables us to infer the mean and standard deviation of the population from the mean and standard deviation of random samples of size n. Theorem 7.1 states that if random samples of size n are taken from a population which has the mean mu and standard deviation sigma, the theoretical sampling distribution of sample means has the mean mu, the population mean, and the standard deviation, population standard deviation divided by the square root of the sample size n. One aspect of this theorem which should not be surprising is that the mean of the theoretical sampling distribution of x bars equals the mean of the population. In our illustration, the mean of the 50 sample means was 68.032, while the mean of the population was 68. A very interesting feature of Theorem 7.1 is that the standard deviation of the theoretical sampling distribution of sample means is given by the formula sigma divided by square root of n. Following the customary symbolism and terminology, we shall write this standard deviation as sigma subscript x bar and call it the standard error of the mean. sigma subscript x bar. We call it standard error of the mean. The standard error of the mean plays an important role in inductive statistics because it measures the variation of the theoretical sampling distribution of sample means. In other words, it tells us how much sample means can be expressed to vary from sample to sample. It should be interesting to check how this theoretical value compares with the value which we actually obtain for the standard deviation of the 50 sample means. Since the population had a standard deviation of 3.44 and sample size n was 5, formula 7.2.2.1 gives 1.54, which is quite close to the value of standard deviation of sample means, 1.66, which we obtained in our experiment. It is apparent from the formula of x sigma subscript x bar, in which sigma is divided by the square root of n, that the standard error of the mean decreases when we increase the size of the sample. This means that when n is large, a sample mean will be a more reliable estimate of mu. That is, when n becomes large and we have more information, a sample can be expressed to be closer to the mean of the population. To illustrate how variability of a sampling distribution decreases with increasing n, let us convert the 50 samples listed in table 7.2.3 into 25 samples of size 10 by combining samples 1 and 2, samples 3 and 4, samples 5 and 6, and so forth. If we calculate the means of these 25 samples, we obtain the figures in table 7.2.4. Sampling distribution of x bars when the sample size is 10. And these values may be grouped into the following distribution given in this table. As can easily be checked with formula for the mean and standard deviation of group data, the mean of the 25 new sample means is 68.03 and their standard deviation is 1.046. This agrees very closely with the theoretical values which we should expect according to Theorem 7.1, substituting sigma 3.44 and sample size n 10 into the formula 7.2.1, we obtain the standard error of sample mean as 1.09. Clearly, there is less variation between the 25 means based on samples of size 10 than there is between the 50 means based on samples of size 5. The standard deviations of the corresponding sampling distributions are 1.046 and 1.55 respectively. Had we begun our experiment with samples of, say, 25 observations, the standard deviation of our experimental sampling distribution should have been close to 0.69. Although it may be important to know the mean and standard deviation of a theoretical sampling distribution of sample means, knowledge of these two values alone will not enable us to calculate the probabilities of obtaining various values of sample means. To be able to calculate such probabilities, we shall have to refer to a second theorem, the central limit theorem, which states, if n is large, the theoretical sampling distribution of sample means can be approximated very closely with a normal curve with the mean mu and the standard deviation sigma over square root of n. A noteworthy aspect of this theorem is that it contains no specification about the population. To be precise, we might add that the population must have a finite standard deviation sigma. This means that when n is large, the theoretical sampling distribution of sample means will be close to a normal curve regardless of the shape of the distribution of the population. Since the n which we used in our example was relatively small, it was equal to 5, let us add that Theorem 7.2 applies also when n is small, provided that the distribution of the population can be approximated closely with a normal curve. As can easily be seen, the distribution of the 9,998 heights given in table 7.2.1 is very close to a normal curve, and this, as well as a good deal of luck, explains why our experimental sample distribution, now look at the figure 7.5, can be approximated closely with normal curves. The diagram shown in figure 7.1 presents the experimental sampling distributions, the histograms. as well as the normal curves, frequency polygons, which approximate the corresponding theoretical sampling distributions. Let us now illustrate how Theorem 7.1 and 7.2 can be used in our problem to calculate the probabilities of getting various values of sample means. For instance, let us find the probability of getting a random sample of size 5 from the population, which consists of the 9,998 heights, for which x bars lies between 68.5 and 69.5. According to Theorem 7.2, we can say that the theoretical sampling distribution of such sample means can be approximated closely with a normal curve, and according to Theorem 7.1, we can say that the mean and standard deviation of this normal curve are 68 and 1.54 respectively. The theorems 1 and 2 can be restated in mathematical notation as the random variable corresponding to the sample means size n is distributed normally with a mean mu and standard deviation sigma over square root of sample size n. Hence, the desired probability between 68.5 and 69.5 is given by the shaded area of figure 7.2. To find the area, we have only to calculate the z values corresponding to 68.5 and 69.5. Then look up the corresponding normal curve areas in table 1 and then take their difference. We thus get the probability of x bar between 68.5 and 69.5, the corresponding z values, and we find the entries corresponding to these probabilities from table 1 and get the value of the shaded area in the figure as approximately 21%. Using the identical technique, we can calculate the probability of getting any intervals in this distribution. In other words, we can calculate all of the probabilities which relate to the theoretical sampling distribution of X bar for random samples of size 5 from the given population. The main objective of the preceding discussion was to introduce the concepts of experimental and theoretical sample distributions. These concepts are of fundamental importance in statistics, and they are by no means limited to the study of sample means. For instance, we could have found the medians of the 50 samples given in the table 7.23 and studied their distribution in order to get some idea as to how much medians vary from sample to sample. This would have given us the distribution on the right-hand side. The distribution of medians, if we had calculated from those values, we can construct this frequency distribution. And its histogram. This would have given us the distribution on the right-hand side. Comparing the experimental sampling distribution of the 50 medians with that of the 50 means, or the histograms of figures 7.3 and 7.1, it is apparent that the first has a greater variation than the second, whereas the standard deviation of X bar is 1.66. It can easily be shown that the standard deviation of the 50 medians is 1.91. This agrees with what we said earlier, where we pointed out that the mean is more reliable than the median, or in other words, that sample means do not fluctuate as much from sample to sample as the corresponding medians. Analog to the theorem 1 and 2, there also exists a theorem pertaining to the theoretical distribution of the medians. As we shall formulate it here, it applies only to samples from large populations whose distributions can be approximated closely with normal curves. Theorem 3. If random samples of size n are taken from a large population, which has mean mu, the standard deviation sigma, and which can be approximated closely with the normal curve, the theoretical sampling distribution of the median has mean m and the standard deviation sigma subscript m, which is equal to 1.25 times sigma divided by the square root of sample size. If n is large, the theoretical sampling distribution of the median can be approximated closely with a normal curve. Since the standard deviation of the population from which we took the 50 samples was 3.44, we should have expected the standard deviation of our experimental sampling distribution of the 50 medians to be 1.92. This is coincidentally almost identical with the value of standard deviation of the median, which was 1.91. It might significantly be somewhat more than or less than the standard deviation of 50 medians, which we obtained. However, in that case, if we had continued the experiment and taken more than 50 samples, the standard deviation of the medians should before long have come close to the theoretical value of 1.92. We could continue our study of sampling distributions while calculating the standard deviation, the range, the mode, the geometric mean, and the average deviation of each of the 50 samples and group them into the corresponding experimental sampling distributions. Then we could calculate the standard deviation of each sampling distribution to measure how much the respective statistics varies from sample to sample. We could also check how close each of these standard deviations is to the corresponding standard error, that is, to the corresponding standard deviation which we should expect according to appropriate theory. Let us conclude our discussion of sampling distributions with the following observation. In actual applied problems, we do not have 50 samples or 100 samples. We have only one. Hence, we shall have to use what we have learned in this lecture to justify generalizations based on one sample mean or one sample median or one sample standard deviation. In practical situations, we cannot repeat experiments 50 times to see how much a mean or some other statistic varies from sample to sample. Next lecture will be on estimation. So, see you then. Bye.